Okay, so today we're going over linearization, or what we call linear approximation. Okay, it's something that we've actually done before, part of it, and now we're just going to use it. So linearization is nothing more than using the tangent line to approximate a curve. Okay, so we're going to linearize the following function at x equals 2. So we have this cubic equation here, and we're going to linearize. Now, the linearization equation itself, okay, that we're basically going to be dealing with is L of x equals f of a plus f prime of a times x minus a. Okay. Now, basically all this is this equation. Y minus y1 equals m times x minus x1. It is the point slope formula, okay, where they've moved y1, so it's y equals y1 plus m times x minus x1. These are the same equation, okay? So just like we used to do with finding a tangent line, the first thing we're going to do is we need to know what a is, or x1. And in this case, it's 2, because that's where we're linearizing. Okay? Then we find f of a, which is y1, which is f of 2. So we plug in 2 into our function. When we plug 2 into our function, we get negative 2. Okay? Then we need f prime of a, which is the slope at a. So we find f prime at 2. So come over here, we find the derivative. So f prime of x is 9x squared minus 8x minus 5. And we use this to find the slope. And when we plug in 2, we get 15. Which means our linearization equation, L of x, equals negative 2 plus 15 times x minus 2. That is my linearization equation. So I've linearized, I've created a line, this line, that describes my function, this one, at 2. Okay? So the thing we know about the tangent line and the function at this point, at the point 2, is they are identical. They are the same. Okay? So basically, when we linearize, we're creating a line that describes the function exactly at that point. And then what we do is we use it to approximate a value close to that point. Okay? So that's the part 2 of this. So we're going to use this linearization equation. So we're going to now use L of x to approximate x at 2.1. So we are going to find what is L at 2.1. So we use our linearization equation. So it's negative 2 plus 15 times 2.1 minus 2. Okay? Which means this is 2 plus 15 times 0.1, which is, negative 2 plus 1.5, which is negative 0.5. Okay? So that means that f at 2.1 is approximately negative 0.5, because L at 2.1 is equal to negative 0.5, which is what we use to approximate f at 2.1. Okay? Now, if you actually came and plugged in, and this is, if you actually find f at 2.1, it is equal to negative 0.357. Okay? So, not a bad approximation. Okay? Now, here's the other thing. The farther we get away from where we linearized. So at 2.1, that's pretty close to 2, okay? But if we got closer to 2, say, hey, what is L at 2.01? So if we plugged in 2.01, we'd get negative 1.85, okay? And F at 2.01 is negative 1.8485, yada, 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 okay? So notice that the closer we get to 2, the closer our approximation gets. And this should start sounding familiar, okay? It's kind of that whole idea when we did Riemann sums or rectangular approximation, where the more rectangles we use, the closer it came to the actual area. It's this idea of limits. And of course, we're using the derivative, which is a limit, to approximate. So the closer we get to 2, obviously the closer the limit is, then the closer the approximation is. Okay? But that's linearization, or linear approximation.